All right, this is Unit 9. So Unit 9, the first half of Unit 9 is going to be looking at thermochemistry, a lot of which we talked about in Chem 1, so that should be a review. And then the second half of the unit is going to be looking at thermodynamics, which is looking at heat and energy and things like that, but applying it to equilibrium and equilibrium systems. And so it's two different chapters. Chapter 5 in your book is going to be looking at the thermochemistry part, and then chapter 19 is going to be looking at the thermodynamics part. This video and the subsequent videos that I'm going to ask that you watch are going to be focusing on the thermochemistry part, and so reviewing many of the things that we talked about in Chem 1. And then in class, we'll be focusing on the thermodynamics aspect and the equilibrium part of it. So the first part of this unit and this video is just going to be a lot of definitions, and so I don't foresee there being these questions on your test or on the AP exam, but these definitions, this vocabulary will be in questions, and so it'll be important that you are familiar with these vocabulary terms in order to then apply whatever the question is asking you to do. So first and foremost, this unit is going to be about energy, and so energy by definition is the ability to do work or produce. And we'll be talking about both of those terms, work and heat, a little bit later. And so energy is the ability to do work or produce heat. The law of concentration of energy, which is also called the first law of thermodynamics, says that energy can only be converted from one form to another. It cannot be created or destroyed. And so you can remember it as the law that says energy can't be created or destroyed. But I'm going to write the other part of the definition saying that energy can only be converted from one form to another. Both are appropriate and correct definitions. It doesn't matter which one you look at. Potential energy, kinetic energy, which, as hopefully you learned about in Chem 1, we're not going to focus too much on either of these in this class. If you take physics or if you've already taken physics, they spend a lot more time talking about potential and kinetic. We will look at kinetic energy a little bit more than potential, but we're not going to spend too much time on either. But it's important that you know the difference between the two. And so potential energy is energy due to the object's position, and I'm just going to use a capital E from now on looking at energy just because I don't want to write the whole word. So energy due to the object position. And kinetic energy is energy due to motion. And kinetic energy is dependent upon two things. And the two things that it depends on are mass and velocity. And the reason for that is the equation for kinetic energy is 1/2 mass times velocity squared. And so both the object's mass and its velocity is going to affect its kinetic energy. Then let's see. So if we look at this picture, this object A is going to have more potential energy than object B simply because of its position. And the object that I'm assuming, because A is held in place, we're going to say that B is moving. And if B is moving, then B would have a higher kinetic energy because it has motion rather than something that doesn't. And so whenever we say that energy is lost, a lot of times is a misleading phrase, because up here we just said that energy can't be lost or created, it can only be converted. And so whenever something says that energy is lost, in quotes, it's not really lost, it's just converted or transferred. And so it can be converted to another form of energy. So, for example, chemical energy can be converted to electrical energy, or the transferred, meaning in this case of the picture, the energy that ball A has is converted into ball B when they hit one another, which forces ball B to then move. And so either that's what it means if it says that energy is lost. It just means it's converted or transferred to another object. And the two ways that energy can be transferred are two things we've already talked about. And the two ways that they can be transferred are either through heat or work. And we'll talk about both of them here in a second. Here we go. So heat is the transfer of energy between objects. The transfer of energy between objects due to a temperature change. So heat is dependent upon temperature. So heat is the transfer of energy between objects due to a difference in a temperature. Work, on the other hand, is a force acting over a distance. And the important part of this definition is this last part, over a distance. And so in order for work to happen, the object has to move. It's got to be going from one distance to another. If it's not, if the position of the object isn't changing, then we say that no work is being done. So for example, if you have object A here, it starts and it goes here. Well, it's changed positions, and so work is being done. However, if object A goes from this point to this point, but then it goes back to its starting point, technically it's distance didn't really change, its position didn't change, and so no work is being done. It's a little bit confusing, but we'll talk about that when we look at the equation used for work. And so just remember that a force acting over a particular distance, so something has to change positions in order for work to be done. At the bottom of the page, we're going to talk about something called a state function, which looks at the pathway that something takes. And so the pathway, by definition, is the route that a system takes. Just like if you were to climb a mountain, the route that you take to get to the mountain, the top of the mountain would be your pathway. The reason why the pathway is important and knowing this word is important is because there are some things that we're going to talk about that are independent of the pathway, and then there are some things that are dependent upon the pathway. And so, as it says here, that energy change is independent of the pathway, meaning it doesn't matter what the route is that the molecules take, the change in energy is going to be the same. It just looks at what the starting energy is, what the ending energy is. It doesn't matter how it gets from point A to point B. It is independent of the pathway. However, work and heat are both dependent on pathway, meaning it depends if you are going from A to B. If you go just in a straight shot, that's going to be a different amount of work and a different amount of heat than something that goes like that. So when we have some sort of quantity, some sort of something like energy or things like that, when it depends only on its present state, it has no effect, the pathway has no effect, we say that it's a state function. And so change in energy is a state function. It is independent of the pathway. We say that it's a state function. But if something is dependent on the pathway, then it's not a state function. And so here, as it says at the bottom, energy is a state function, but work and heat are not. One way that often helps, at least me, and hopefully it helps you figure out whether or not something's a state function, is if you look at its symbol. If the symbol for whatever thing you're talking about is a capital letter, it's going to be a state function. And so things like energy, that's a state function. If you remember enthalpy from Chem 1, which we'll talk about in the next video, enthalpy is written as a capital letter. That is a state function. But if the abbreviation for a term is a lowercase letter, then it is not a state function. So work is a lowercase w, heat is a lowercase q. Those are not state functions. So capital letters are state functions. Sorry about that. And lowercase letters are not. So these are dependent. And that might help you a little bit with the difference between the two. And if you remember, you'll see this later on in the unit, but if you remember from when we talked about kinetics, so thermodynamics oftentimes looks at the beginning and the end. It doesn't care how it gets there. And so most of the things we're going to talk about in this unit are state functions. They only depend on their present state, what they started with and what they ended with, not how they got there. All that stuff in the middle is what kinetics is all about, the pathway. And so we will talk about some path dependent things, but not nearly as many as we will talk about for state functions. All right, next, the definition between system and surroundings. And so it's important to know that we focus on the system. And so the system is the part of the universe that we care about. And more specifically, it is the reactants and products. It is the actual substances, the molecules that we are talking about. Everything else is going to be part of the surroundings. Remember that chemists care about the system. Chemists do not care about the surroundings. If you're taking a POE class or some other engineering class, remember engineers care about the surroundings, whereas chemists care about the system. So everything, unless otherwise specified in this class, is going to be referring to the system. If it's talking about the surroundings, it will specifically say surroundings. All right, exothermic and endothermic. Hopefully these are terms that you remember. So exothermic is when something has energy flowing out of the system. Energy is leaving, it is exiting the system, whereas endothermic is the energy is being absorbed by the system. It is entering the system. Whenever you have an exothermic energy, an exothermic reaction, there's energy. And so this energy that is leaving the system, where is it coming from? Well, if you think about a potential energy diagram, the products here have a lower amount of energy than the reactants do. And so the extra energy that is being released is that difference in energy from the reactants to the products that the products don't actually need. And so it leaves the system. So in an exothermic reaction, products have a lower amount of potential energy than the reactants do. And so the extra energy that isn't needed is what exits the system. And the last thing that we're going to talk about very quickly is just the opposite. So where does the absorbed energy go to? Well, the products have more energy, and so that extra energy that's being absorbed goes to the formation of the product.